Okay. So our next speaker is from Mentor Graphics, Avidan Efody, who's a verification architect. The title of his talk is Fault Analysis. What is your real FIT size? Avidan Efody is a verification architect for Mentor Graphics and an expert in listening to customers, distilling their problems and helping them to get an optimal solution, preferably using Mentor tools. Prior to moving to EDA, Avidan has been architected and coding test benches in a variety of languages and methodologies for a variety of companies, including PMC, Sierra, Infineon, TI, Nokia, Siemens, and others.
Thanks, Mike. So I'm sorry you will have to suffer with an Israeli accent for another presentation. I hope it's not too bad. I'll try to work on my R. So so the title of this talk is Fault Analysis, What is your real fit size? That was a sort of a little word game. And if you know the ISO 26262, then you know what fit is. If not, then you will hear it very soon. Since this conference is verification futures, I thought I would, look up somebody who is an authority in predicting the future. So I opened, Nostradamus, our old pal from 2000. So I think he screwed up when he said that the world will be, gone at 2000, but maybe let's give him another opportunity. So I looked up and I found these two slightly enigmatic sentences. So dysfunctional verification is the new challenge, and reliability is the new power. And then I spent 2 weeks to thinking what could these sentences mean. So what is dysfunctional verification? So functional verification, we all know what it means. It means that you take the spec, you read it very carefully, and then you try to make sure that your design does whatever the spec says. And if there are errors, let's say, in the spec, there are error conditions that your design should handle, then these errors are specified by the spec. And, for example, if you have, let's say, a packet and it comes with a CRC error, then the behavior for this packet with the CRC error is specified. You will know that the packet should be discarded and that it should, let's say, be counted by a counter. But this functional verification is a much wider scope, right? This functional verification means that the design, the components of the design don't behave correctly. So you have gates that all of a sudden change value, for example, right? You have flip-flops that don't behave like they should. You have state machines jumping from one state to another. It's a totally different problem to solve. So in a way, with normal verification, it normally stays below the cut line. I mean, who would be crazy enough to verify a situation where a state machine jumps without reason from one state to another? But in these days, and especially for safety standards like ISO, this is what we are required to do. So this changes the rules of the games. Nothing is basically the same. So if you look at the stimuli, what is the stimuli? The stimuli is not constrained random in UVM. Some of you might find this a good. Some of you might find this a good news. What is meaningful coverage? We have, there is such a wide, oh yeah. So we have such a wide coverage space now to cover with all this dysfunctional behavior that we need to cover. What does it mean? How do you analyze the results? So let's go through quick basics. Here is the aim, and here is where we get to the fit part. So with this functional verification, what we want to do is really make sure that the mean time between failure, that's the known concept, or by ISO, the equivalent of this is the failures in time, or fit, is below a certain threshold. So that's the aim of what we are after. We are not after full compliance to the spec. We are not after showing that there are no errors. We just want to show that the failure the failures are below a threshold. And then the means to do this is by taking a statistical sample of all the faults, and we cannot cover all the faults in the world, right? So we have to take a statistical sample, and we have to analyze them and see if they are good or bad, if they evolve into something that is terrible, into an accident, or they just end up being masked somewhere along the way. And there are some other vocabulary that I found a little bit hard to come by, so I thought that it could help you as well. So fault model, for example, is the way that things break. So I see that many of you have glasses, just like me. Most people that don't have glasses think that the way that glasses go bad is when the lenses break. But this is not true. Actually, the first part that goes bad is this part, right? The handle breaks, especially if you have kids and they like to push this. So this is a fault model for glasses, right? That's how glasses end their life. Flip-flops are the same, right? Or gates in a design are the same. They have fault models. So they have various ways, typical ways in which they can go bad. And this is, if you take now the fault model and something happens, this is the fault, right? The fault model, if a FIFO goes bad in some way, it's a fault. If it causes an accident to happen, if it causes some failure, if it causes something critical to happen, then it's a failure. In between, there is this stage where it becomes an error. An error means that the fault has progressed enough to become dangerous, but it's not yet there. So once again, going back to my glasses are already at the error stage. So my kids are almost there. A little bit more trying, and they will they will break them. So the problem we are trying to solve with dysfunctional verification is really showing that this elephant can fit into this hole. And how do we do this? This elephant is called your base fit, your base failure in time ratio. And it is made out of many fault models whose probability, at the worst case, is very, very big. So every flip-flop could go bad in a given probability. And then you take your million flip-flop design, and you multiply that, and then you get a probability that no automotive standard will accept, right? It's not accepted. So the base fit is very, very big, just like your base salary. Base salary is big, but then, something bad happens. So what do we do about it? What is the game that we play? The game is called derating. So we try to derate these faults and show that most of the faults are not relevant and that they will not really cause a failure. So there is a way to do timing derating. You show that a fault, if it arrives at a given point between setup and hold, then it will propagate. But every other place, it will not. So that removes part of the fit. And then you can show that if a fault gets into a gate, but the other input to the gate masks it, then you have then this fault will not propagate, right? That's called logical or sequential derating, and that removes many other faults. And then you can do use case derating, and there are many more ways to do derating of faults until the elephant gets just the size of the hole, and then you can push it in. So just an example of how this works, looking at logical and sequential derating. If you have this gate that is going bad at time 0, and then it propagates all the way to the flip-flop because the conditions are favorable, then basically it becomes an error. But it cannot, at this case, for example, it will be masked along the way because in the next cycle, it is overridden by a value that is good, and the next MOOCs is not leading it to the safety critical area, and this fault can be considered a safe fault or a multi-point fault according to ISO, and I will talk about it in a second. And then there are other cases where the fault will propagate to a safety critical area, and that should be counted as a dangerous fault or as a single point fault according to ISO. So ISO really asks you to analyze these sorts of faults and say, what are they going to lead to? And if you think about it, a little bit, then you realize it's very, very similar to X propagation problem. So what we want to do is we want to inject X's in some gates or in some flip-flops to simulate the faults. And then if the X propagates to the safety critical area, then we're screwed. If the X doesn't propagate there, then it's masked, and you can periodically check if the X is still in the system to know if you've gone from a faulty state into a normal state again. So ISO, now I'm talking specifically ISO 26262 asks you to do this fault analysis very rigorously, and it asks you to categorize the faults into different buckets. So one bucket is single point fault. Single point fault is bad. It's a fault that propagates all the way to the safety critical area and doesn't see any safety mechanism along the way. Safety mechanism means something like parity, something like ECC, something like a lockstep comparator, nothing like this along the way. Bad. We have residual fault. It propagates to the safety critical area, and it goes on its way through a safety mechanism. But the safety mechanism doesn't work for this kind of fault. Maybe the safety mechanism is a test pattern that runs every once in a while, and the fault has happened in between the test pattern running. So residual fault, also bad. We have multi-point fault. That's a nice part about ISO. It always likes to look at the half glass empty. So multi-point fault, you would think it's good. It's a fault that happened somewhere in the design, and then the safety mechanism really caught it. Great, right? But no, it's called multi-point fault. Why? Because if another fault will happen in the safety mechanism, then it will propagate. But it's still a good place to be. Detected if the safety mechanism shouts something about it, and latent if it just swallows it and nobody knows about it. And then there are many, many questions. I mean, there is a great LinkedIn group to discuss ISO and fault analysis, and there are many, many questions that come up about this definition. So, for example, just to take one, if you have a stacked fault, so a gate getting stuck at somewhere, and then it can propagate to the safety critical area. That will make it a single point fault. But if you're running a test pattern, this test pattern might catch it, and then it becomes a multi-point fault. So what is it? Is it a multi-point fault? Is it a single? Is it both? Hard to say. There are many, many more questions like this. So I've so far, showed you a little bit, gave you a taste a little bit of the challenges and the methods that we're using to analyze faults. But the elephant in the room is really, the big question here is really what happens after all this effort. You are trying to squeeze the elephant into the hole, and you are trying to derate in this way and that way, and nothing works. It's still too big. What happens then? So basically, it's not good, right? That's the scenario you'd like to avoid. What happens then is that you have to really go back to square one. You have to rethink your safety concept, rethink about your safety mechanisms, and think if they are doing their job properly. And then once you do all this rethinking, you have to re-implement and re-verify. So it's a lot of work that needs to be done pretty late. Why pretty late? Because the accurate measurements, they come from gate or RTL. So it is similar to power. And maybe that's what Nostradamus meant there. Reliability is similar to power. It is not yet supported by the flow in the industry. There is no equivalent to UPF. There is no URF, Unified Reliability Format, or anything like this, but it's coming up, right? It's similar to power. You have to plan it from the top, from the high-level models, from the spec, from the high-level models, all the way down, RTL gate, make the measurements at gate, and then hope they are not, they conform to your high level. So that's where we are probably going. So to wrap up this short talk about safety and fault analysis, safety cannot be added on. We know that. That's a sort of axiom through we know that a lot. That's what ISO does for you. ISO basically makes sure that you don't try to add safety on. if you try to add safety on, let's say at RTL or gate, you can do a little bit, as always at RTL at gate, but you cannot do too much, right? So the playroom is really if you start with safety all the way up. And then the challenges we have are just like the challenges. One of them is like the challenge with power, and that's smooth transition between abstraction levels, right? You go from the top level abstraction to the level below it, to the level below it, and you make sure that the results that you get at each abstraction level, they are actually the same results. And I would like to finish with an optimistic note that safety and security are great news for all of us. I think Mike realized this very early on and is riding the wave. It opens so many possibilities, so many new possibilities. Dysfunctional verification is so much wider than functional verification that we are going to have work for many, many more years. So, yeah.
Thank you. Yes, we have time for a question.
So actually just two quick questions, interesting talk. The first one is you were talking a lot about how we're trying to catch these faults and model these faults and things and trying to prevent these from getting into safety critical areas of design. So how do you know that that safety area is safe and that you're not going to have errors in that barrier that's allowing this through? So that's the first question. And the second question is, how detailed do you actually go into the fault modeling? So, for example, do you take into account things like short channel effects as technology nodes get smaller for testing these different things?
Okay, so first, thanks. You were one of the only ones that didn't fall asleep. I saw some others, so I appreciate it. So I think there is no such thing as you can be sure with this kind of problem. We cannot be sure that actually the safety mechanism works. That's one of the problems. So we have to apply the same analysis to the safety mechanism itself, right? And also, you know, make sure that ask ourselves what happens, what probability of error are we getting if parts of the safety mechanisms are, you know, stacked or have transient faults or so on. So that's an interesting question in its own right. And now to your second question, the level of detail is really, you take everything into account. You use everything that you have in your arsenal. I mean, the effort in analysis is really to prevent over-design, right? You don't want to put 1,000 safety mechanisms. You really want to estimate your derating well, right? So the more accurate models you can use, the better, right? And of course, you take node into account, you take a capacity, you take everything into account. Even at the structure of the cell, sometimes the cell itself has trade-offs between power and reliability, right? So it's applied by fabs and everything. So whatever you can do, you do it. So.
Thank you. Any more questions? Just one comment as well. I do think safety and security are the future. Our devices will be going to lots of areas where safety and security is going to be very, very important. So thank you for the talk.